Hello, and welcome to this lecture in dynamics. In the past few video lectures, we looked at first kinematics, in which we applied ourselves to one dimension, defined the average speed, and then we said that as the change in time goes to zero, that is the limit of delta t going to zero, that becomes an instantaneous speed, right? And we did a problem here looking at just the idea of integration to find out the total distance. And average acceleration was an extension of that same idea, where now we have the change in velocity over a finite amount of time is average acceleration, while instantaneous is over an infinitesimally small amount of time, that is as delta t goes to zero. And the idea is that you can go from acceleration to velocity by doing an integral, and from velocity to position by doing another integral. And the opposite direction, you can do it using differentiation, right? So we did a problem here, and then we noticed that these formulae that are very familiar to you are only applicable when the acceleration a is constant. Okay, that's an important aspect to keep in mind. Everywhere else, you will have to go through this process of integration to the right or differentiation to the left. With all of that, we then move to planar motion, where we move away from just movement along one dimension to now having a plane in which you can move, or in that case, you would have to define two coordinates, x and y, and that essentially sets up a vector as a quantity with both magnitude, which is like this distance, and the direction, which is this direction. Okay, so we did a review of vectors, and today we are now going to come back to the idea of differentiation. First, let's just review that in the sense of scalar differentiation. So take a moment to try and recall differentiation. That is the differentiation of some function that is f of x is equal to f of x plus h minus f of x divided by h as h goes to zero. Right? What does this mean? If you have a function, any function, in this case, it's a function f of x, and you now have something that looks like this, perhaps. You then have the value of the derivative at any instant is the tangent to the slope of this, sorry, the tangent to the curve. So if this here is some position and you go a distance of h away from it, so let's say this here is h, this here would be f of some x plus h minus f of x, and that sets up a slope, right? But this slope is between these 2 points. Now, as h becomes smaller and smaller and smaller, is essentially the tangent that you obtain at any point. So the tangent over here would be this, and that is what is the value of the derivative of the function. Okay, the slope of that tangent line. It's always the slope of the tangent line. Now, how can we use this? If ever you want to find the maxima or the minima, which is these points, so the points where the slope becomes zero, so this point over here and this point over here, they are maxima. Um, this point over here is a minima. So in cases where you have d over dx, that's the derivative of the function f of x with respect to x, is equal to zero, it's either a maxima or minima in this class. There's also something called a saddle point, which we are not really going to look into. How do you know if it's a maxima or a minima? So at the maxima, your slope going from left to right would initially be positive and it'd be decreasing until it becomes zero. and then it is negative, right? So you know that the slope of this line is positive and the slope of this line is negative, right? So here the slope is positive, and then the slope decreases until it's 0, and then it becomes negative. So that means that the slope was positive and then becoming negative, which means that at the maxima, the rate of change of the slope, which is essentially the second derivative, is less than 0. Why is that? Because the slope is decreasing. You see that? In a minima, your slope is initially negative and then it increases until it becomes 0. The flat line has 0 slope, and then it keeps increasing. So it's been increasing throughout. So here it is d2 dx2 f of x must be greater than 0. Okay, so with this, you can now identify points that are either maxima or minima in your function. Let's apply that directly. So a particle's position is given by s of t is equal to 5t minus t square. We want to know what is the farthest point that this particle will reach. So how would you do this? You only have to apply what is above, but read the question carefully and try to find the answer. Pause the video and come back to the solution as I discuss it. Okay, so we're looking for the farthest point, which means we're looking for the maxima, which means we need to find first d dt of s is equal to 0 and d2 dt2 of s must be, so it says farthest, which is like the most, the maxima, must be less than 0. Okay, so first let's find what is this here. This would be 5 minus 2t is equal to, and this here, the 5 minus 2t is equal to 0 at t is equal to 2.5. What is the second derivative? d2s dt2. This here is minus 2 is less than 0, which means that at t is equal to 2.5, the maxima is reached. Okay, if this had some variable as say t or something, you need to substitute this value here to then check what is the value of d2 as dt2. It must be less than 0, then it is that the maximum is reached. Okay, so in this particular example, it happened to be that this was just a number. Okay, so for example, if this was t cubed, then this would be 3t squared. And now when you do the differentiation, you will get minus 6t. So you see that there is a t remaining over there. Now, whatever is the position of your location where the slope is 0, you have to substitute that t there to then check it. Okay, keep that in mind. Does this answer your question of what is the farthest point reached by this particle? It does not, because the question doesn't ask you at what time does it reach that. It says what is the farthest point. So the value f of t at t is equal to 2.5 is the farthest point reached. So there's essentially f of 2.5, that is 5 times 2.5 minus 2.5 squared, which is 6.25. So whatever the units, 6.25 is the maximum that is arrived at by this particle that is traveling according to this position. Worth noting here is that when you say that this ds dt is equal to zero, it's essentially saying that the velocity is zero, right? So every time that the particle is at rest, it is at either its maxima or its minima. In this case, it is the maxima because you have that the second derivative is less than zero. Okay, that's a bit of a review. Let's now move to vector differentiation. Okay, so what was our definition for instantaneous speed? Let's just write that down over here. We'll use that as a reference. So this was limit delta t going to zero, delta s over delta t. Right, that was v is ds dt is equal to the above. Let's now look at the same idea but applied to vectors. Okay, so um, you have one vector here given by r of t, so that's the position. Okay, and this here um, is at time t, and at time t plus delta t, it has now reached this position. So this is r t plus delta t. And what then is this vector here? So this would be r of t plus delta t minus r of t. That is the displacement vector if these were position vectors. Okay, so position vectors are in general defined from a known reference point. So this would be some origin O, and this here is I hat, J hat perhaps. And you're tracking some object, and this object has been moving in a path that maybe looks like this. Okay, so this is the path of the object. At time t, your position vector was pointing this way. At time t plus delta t, it was pointing this way. Okay, and somewhere in between it would have been pointing here and so on. Now, this here is a part of the particle or the object that is moving. And what we're now interested in doing is obtaining the velocity. Okay, so we know that the average velocity is going to be delta r over delta t. So as you can see here, it is a scalar value. So speed is scalar, it's a magnitude. While here now with velocity, we're defining it as a vector. Okay, so this is essentially r of t plus delta t minus r of t divided by delta t. So essentially looking at this, that is the average velocity from here to here. So it has a direction and it has a magnitude. Okay. Um, so above is vector, and below this delta t is of course a scalar. Okay. Now, if you were to convert this to instantaneous velocity, which is by definition, if you just called it velocity, this is dr over dt, which is the limit of delta t going to zero of the same difference divided by delta t. So this r of t, if you were to look at the next time instant that's very infinitesimally small time instance away, then your instantaneous velocity would be oriented in this way, and the magnitude will be defined by the magnitude of this vector divided by delta of t. Okay, and the speed is essentially the magnitude of the velocity vector. So the velocity vector is what we just defined here, and this here is essentially the differentiation of the position vector. We can extend this same discussion to acceleration, where again the average acceleration is now dealing with, instead of position vectors, we are then dealing with velocity vectors. So at the instant of t plus delta t, what is the velocity? If it was something like this, this here is your velocity at t plus delta t, and I have velocity at time t as this here. So this is v of t plus delta t, and this is v of t. Now, what vector would represent this? Is it this way or is it this way? Take a moment to try and find that out. So essentially, this would be v of t plus delta t minus v of t. You can always verify it as you have this vector plus this vector, it should equal this vector, right? So this is v of t plus delta t minus v of t, so these two cancel out, and then you have just v of t plus delta t, which is what you see here. Okay, so that is your average acceleration, and of course your instantaneous, which is a vector instantaneous acceleration is going to be d over dt of v as a vector, and the same relations as we defined above. There's no different word for the magnitude of acceleration. It would just be called the magnitude of acceleration. Okay, so this was just defining the velocity and acceleration as now vector differentiation. If we have the case where, let's say, um, unit vectors remain fixed. So we're just going to do this for velocity, for example. We could do the same thing for position vectors as well. But you have velocity as v of t, and this here has components along the x, y, and z. So I'm just going to define some unit vectors first. Let's say this is I hat, this is j hat. In what direction would k hat be? It would be outwards. So this here is I hat, j hat, and I have k hat coming outwards. So there are components, and I'm going to draw those components now. So this here is v along j hat, right? So this here would be vy of t, and then there's a component here. I'm trying to draw it as parallel as possible. So there's vy of t upwards, and then there is a vx of t in this direction, and then there's a vz of t in this direction. So essentially, this component along vx plus this component along vz, this component along y, are what constitutes this vector defined along these unit vectors. So that is at time t. Let's now define the case for time t plus h. Just drawing something as a different vector at time t plus h. Okay, these are vectors. And I'm trying to get the components again. In this case, let's say that this much is your Vy component, and you have this much as your x component, and this much as your z component. So this here is Vx of t plus h. Sorry, there's Vy t plus h. This here is Vx of t plus h, and this here is Vz of t plus h. Okay, so what's happening here, and the reason why I did all of this, is to now try to define this vector, which is the difference, right? So this would be delta v. So essentially v of t plus h minus v of t. And we're going to look at what appears when we do the vector differentiation. So if we were to do d over dt of v of t, this is limit of h tending to 0, v of t plus h minus v of t whole divided by h. And we have already broken down these vectors into its components. So I can then write this as limit h tending to 0. V of t plus h is vy. I'm going to do it as x first. Vx of t plus h along I hat plus vy t plus h along j hat plus vz t plus h along k hat minus your vx of t I hat, vy of t j hat, vz of t k hat. Remember that this is all divided by h. We can always group the terms together. So then you get limit h tending to 0. I now collect all the I hat terms. So it is vx of t plus h minus vx of t over h in I hat. I'm going to have limit h to 0, vy of t plus h minus vy of t over h, and limit h to 0, vz of t plus h minus vz of t over h. We're able to do this because everything is written in terms of I, j, and k. Okay, and you can now see that this here is essentially the differentiation of the the x component, that's vx of t along I hat. This entire thing is, well, I should have written j hat here. Sorry about that. Should have j hat. This here should have k hat. This is the differentiation of the y component. So y of t becoming y of t plus h. So we're looking at only that components change, and this can be written as a differentiation of vy of t j hat. And now this one, if you look, just it's the definition of the derivative of some function. So it's like the differentiation of vz of t along k hat. Okay, so when the unit vectors are fixed, then and only then can you take the derivative of the vector component along each unit vector. Okay, so this here is what we've just arrived at. So when unit vectors are fixed, what does that mean to say unit vectors are fixed? Unit vectors by definition have a magnitude of 1, right? So when you say it's fixed, all it means is that the rotation does not exist. So unit vectors are magnitude and direction. By definition, unit vectors have magnitude 1. So it's just a direction. And if this direction does not change, it remains in the same direction, then it means that the unit vector is fixed. So I'll write that in brackets. No rotation. Um, when unit vectors are fixed, then the derivative of vector components along each unit vector yields the vector derivative. Okay. So let's just do a problem to make sure we understand this. So let's say that we are working in 2D. Okay. Um, you have a point O, and you're able to throw a particle at some velocity of v naught. This here is velocity v naught. This is angled at some theta with respect to the vertical. And there is wind that is blowing. Okay, so I'm gonna say that there's wind blowing in this way, just creating an acceleration. And there's also, of course, gravity that's acting. So wind here is generating horizontal acceleration of 0.4 meters per second square to the left. Uh, what angle theta will result in the particle returning to the same position if, and I'm not giving you the magnitude, v naught magnitude is equal to 12 meters per second. Remember, you cannot neglect gravity. What you're doing now is you're just going to apply the ideas of, um, going from, where did we do that? Yeah. So going from acceleration to velocity by integration, and from velocity to position by integration. Except previously we did all of this in just one dimension. Now, based on this result that we've obtained, you can now do it on each dimension. Okay, take a moment to try and solve this yourself. Okay, so first we write down the acceleration. This here is minus 0.4 I hat plus minus 9.81 j hat, because this is in meters per second squared. Um, I hat and j hat are always going to be along these directions. So this is I hat, this is j hat, and k hat is outward. If you want any other unit vectors, maybe you could define an x hat and y hat, however you like it. Um, but unless you draw I hat and j hat, you can assume that they're going to be horizontal and vertical. Okay, so now that you have the acceleration, how would you get the velocity? You want to integrate, right? So this here is equal to dv dt along x I hat, and this here is dvy dt along j hat, which means I could then write dvx is equal to minus 0.4 dt and dvy is equal to minus 9.81 dt. If I were to do the integration, now do you apply v naught here for both? Think about that. So in the vx case, you want to have the x component of v. So that is, in this case, v naught sine theta. So it will be from v naught sine theta, which is 12 sine theta at time t is equal to 0, to whatever is vx, and this here would be to time t. Similarly, for vy, it would be v naught cos theta to vy, going from time 0 to time t. So essentially, you get vx is equal to, well, I guess I can write it fully. So vx minus 12 sine theta is equal to the integral of this, that is minus 0.4 t. And you have vy minus, I guess I can write this as 12 cos theta is equal to minus 9.81 t. And with this, you have then that vx is equal to 12 sine theta minus 0.4 t, and vy is equal to 12 cos theta minus 9.81 t. Okay, this is a little unnecessarily long. I would rather just write it as initial condition for each. So this here is the initial condition, right? 12 sine theta, and then the integration of this. So this is minus 0.4 t I hat, and then initial condition for y, that is 12 cos theta, plus the integral of the acceleration term, so that's minus 9.81 t. Okay, so this here has given you the velocity. See if you're done. No, the question asks you about when will the particle return to the same position. So that means you have to do one more integral to obtain the position vector. So that is r vector is equal to. And now you could do all of these steps, or you could do what I just said, which is write down the initial condition. So it starts at 0, right? So 0 plus the integral of the above is 12 sine theta t minus 0.4 t squared by 2, or 0.2 t squared I hat. It starts at 0 because that's what we're assuming to be our origin. And then you have, for the y component, starts at 0 plus 12 cos theta t minus 9.81 t squared by 2, or 4.91 t squared j hat. Okay, so now you have the position of the particle at any time. So it's going to be something like this. And there's one component due to acceleration, there's one component due to gravity. They're looking for something where your particle moves in this manner, right? It has to come back to this. So what does that mean to say it comes back to the origin? At the time of interest, this here would be 0 and this here would be 0. So you have two relations. Um, First, 12 sine theta t minus 0.2 t square is equal to 0, from which you can then rearrange the terms to obtain sine theta is equal to 0.2 t over 12. From the right hand side, when you get 12 cos theta t minus 4.91 t square is equal to 0, how can you apply sine theta over here? You have cos theta, right? I would like to use sine square theta plus cos square theta is equal to 1, which means if I can then write that cos theta is equal to, it will be 4.91 t over 12. That now allows me to write that sine square theta plus cos square theta is equal to 1, or 0.2 t over 12 plus 4.91 t over 12 whole square, of course, each of them is equal to 1. And this will give you, if you were to solve this, you will get 24.148 t square is equal to 144, giving you t is equal to 2.44 seconds. And is that the answer that we're looking for? No, the question asks you what is the theta that'll do it. Right now it's telling you what is the time that'll do it. But of course, you can just substitute this or into that, and then do the arc cos or the arc sine. Let's do it for cos. So cos theta is equal to 4.91 times the t that we found divided by 12, giving us theta is equal to cos inverse of 0.99917. The reason why I wrote so many is because it's going to be very close to 0. So we want to have as many significant digits as possible, giving us now theta is equal to 2.33 degrees. Okay, I hope I did this correctly. It means that your theta has to be really small. Well, I guess the acceleration here is very small as compared to this. Right, this is 9.81, the 0.4. So I guess it makes sense that it'll be a very small angle. It'll come back to its position. Okay. So that was kind of the process of how you would approach this. You always want to be cognizant of what is it that you're looking for. You're asking for what is the angle. As you were going through, you realize that you have to do two integrations. So you obtain the velocity and then you get the position. But essentially, anytime you have acceleration and you have an initial velocity, you can then find the velocity representation. And then from that, you can obtain the position representation. And then you can make use of that in any way that is of interest. Okay. Again, if you have any questions, email me. I hope I didn't make any mistakes, but let me know. The next question deals with projectile motion. So we have the ground and we are throwing some object at an angle of theta with an initial velocity of v naught. So this here is theta with respect to the ground. This here is a velocity vector with a magnitude of v naught. Okay, so I'll just write down the question now. The question is, what theta maximizes range? Okay, so think about this. You have an initial speed of v naught that is fixed. So it's like you have a cannon or a gun or something, and you are able to uh, launch or shoot something out at an angle of theta. This theta you can vary. So your cannon can be pointed in whatever direction you want, and you're only able to change theta. Your initial velocity remains constant, and then, of course, if you are familiar with physics, you will have that this is going to land at some point here following this kind of a motion. And the question asks you for what theta maximizes the range. So range is essentially from this point at what position will it reach. So you want to find first an expression for range, and then you want to find theta that maximizes it. So you're going to apply what we just discussed over here again, now with the context of maximizing range using theta. Okay, pause the video and try again. Okay, so let's write down what we have. So we have acceleration is minus g j hat. The velocity v is going to be first along the I hat. It's v naught cos theta along I hat. And there is no acceleration in this direction. Unless I specify, there's no drag or something like that that you have to account for. And then you have v naught sine theta along the I hat j hat direction minus gt along j hat. So now you have the velocity. Is that enough? No, the question asks you about the range. So here's your position vector for range. This is going to give you, if you integrate, you will get v naught cos theta t. Why is it that? It's because the initial position is assumed to be 0. So it's like you defined your origin as O. And then again, along the j hat, you have that the initial position is 0. So 0 plus v naught sine theta t minus gt square over 2 j hat. What is the meaning of range? It's essentially this, but it is when t is such that this has been come back to 0. So tf is the final time such that v naught sine theta tf minus g tf square over 2 is equal to 0. Essentially, r is going to be equal to v naught cos theta tf. Let's first look at defining tf. We'll very quickly find that tf is simply 2 v naught sine theta over g. That's just by, you move this on the other side, so you get this is equal to g tf square over 2, and such that so long as tf is not equal to 0, these vanish, and then you have tf is equal to 2 v naught sine theta over g. That means that range r is equal to v naught cos theta times tf, that is 2 v naught sine theta over g, which is going to give you 2 v naught squared sine theta cos theta over g. I'm going to write it as v naught square 2 sine theta cos theta over g. Why did I do that? That's because this here is sine 2 theta. So I can write as v naught square sine 2 theta over g. So what is the question? Again, the question asks you what theta maximizes the range. In this case, we're looking for the maximum value of this here. It's like you have a function that's varying based on theta, and this function, whatever it is v naught square sine 2 theta over g. So how would you find the maxima? That's where it's maximum, right? Take a moment, pause the video, try it yourself. We've just discussed this. Essentially, you're doing d theta of r. Why are we doing it with respect to theta when previously we did it, right? Here we did it with respect to time. It's because in this case, this function is a function of time, and as time varies, this position changes, and we're looking for what is that position. In this case, we're looking for the range r, which varies not with time because the time aspect is already defined. You see, it lands at a certain time. We found what is that time, and then we substituted that back here, and then we simplified and found this. It does vary based on theta. If your theta was really small, it'll be something like this. If theta was larger, it'll be like this. Okay, but if it's too large, it comes back here. So there is some place where this theta causes maximum range. That's what we're looking for. So here, dr d theta will give you what? Take a moment to think. V naught is a constant, g is a constant. You will get V naught square over g cos 2 theta when you differentiate with respect to 2 theta, and then you do have 2 coming out because of the chain rule, right? Just going to rewrite this to be a little more clean. So you have this here. This is equal to 0 at maxima or minima. You know that there's only a maxima, there's no minima, since uh, this function is defined for this kind of a motion. It's not going to go into the ground, and then you'll have a minima. So in this case, we can say then that cos 2 theta has to be equal to 0 for this to happen, which means 2 theta is equal to 90 degrees, which means theta is equal to 45 degrees is what maximizes your range. Okay, I hope this made sense. Let's now change the orientation of this question. So I'm going to make it that we are now on a slope. And this slope here, so the way that I'm going to define this is that theta is still with respect to the horizontal. Let me draw it here. So theta is with respect to the horizontal, and alpha is the slope of the plane on which you're throwing this. So in this case, now again, you will have, your particle is going to move in this projectile motion kind of a thing. But let me try and draw that better. But now it's going to land on your slope. So same question again. Projectile launched at angle theta and speed v naught. What is the theta that maximizes the range? Remember that we're defining theta with respect to the horizontal. That actually makes your calculations easier because essentially now let me fully define the question. Define the range theta. Define, yeah, what theta maximizes range, where that's just completing the question. So try this again. Take a moment to pause the video. Okay. First, is there anything that changes in what we did over here? Theta is still defined with the horizontal, and so everything that we did above remains as is. The only thing is that previously we had that this here was going to 0. Now what are we doing? We're trying to find the maximum range. So this range here would be something like what I've shown here. R. We're looking for what is R max, right? So previously this was going to 0. Instead of that, now what we have is that this here is going to be R sine alpha, right? So this is the y position at any instant of time. So at this point here, this component, so at this point here, this is your j hat component, which is going to be v naught sine theta t minus gt square. When it is over here, that is when it has landed and it's back on the ground. Now, well, back on the slope. Now this height is going to be r sine alpha, okay? And what about this here? That is your x component. So here, your x component was defined by v naught cos theta t. At this point, it would be r cos alpha, right? So that is essentially the constraint of having it fall back onto the slope. Okay, so these are the two relations that we have. There is one variable theta and there's a variable t. You now have two equations, two unknowns, and so we can solve this. So essentially at tf, we have v naught sine theta t minus gt square over 2 is equal to r sine alpha. Um, if you were to now uh, look at the x component, you have v naught cos theta, and well, I guess I should write these as tf. Tf is equal to r cos alpha. So can you now simplify and find out what is r? I think it's easier to substitute tf from this into this. So what I'm going to do is write tf is equal to, you'll have r cos alpha by cos theta divided by v naught. And this tf, if you were to substitute back up, you will then get v naught sine theta r over v naught cos alpha over cos theta minus g tf is r square cos square alpha. Don't forget there was a 2 here. This here's v naught squared. This here's cos squared theta is equal to r sine alpha. It looks like there's r everywhere, so long as r is not equal to 0, which is an uninteresting problem, we then have r cancelling, and then we can then focus on this r and rearrange everything so that we can obtain something useful. You will get r is equal to, you can get 2 v naught square cos square theta over g cos alpha times tan theta minus tan alpha. Okay, because you'll have sine theta, cos theta, and sine alpha, cos alpha appearing. So you get this as your range. Again, are we done? We're looking for what theta maximizes the range. So in this case, again, we have to do dr d theta is equal to 0. I'll leave this to you as a challenge for you to solve. I'll give you the answer. You will get theta is equal to 90 plus alpha over 2. The question asks you for what is the theta, and to this, here's your answer. If you substitute this, you will get R max, but that was not the question. Um, Take this as your challenge. Try to do it yourself. You're differentiating with respect to theta. You will have to use a product rule. Remember that these terms are all constants. Okay, so essentially it's just this over here um, as a product rule, and the other one will be just cos squared theta tan alpha. So you should be able to differentiate this, set it to 0, and you will get this as your answer. Um, can we do a sanity check in some way? If you had that alpha was equal to 0, that is this alpha 0, then essentially you have the same problem as above, right? And so your theta becomes 90 by 2, that's 45. And so yeah, you can, that's a sanity check to say that what we've done here, it also applies to this simpler problem that we just discussed. Okay, I hope this makes sense. As you can see, the case where your unit vectors are fixed, that is stuff like what we've seen here, it's rather straightforward. You just have to do integration, differentiation, and apply it to the constraints of the problem, and you get the answer. But it's not particularly interesting. It might be very similar to something you've already studied in physics. And for this reason, well, not only for this reason, you can apply this to pretty much a lot of problems. Uh, in the future classes, we'll be looking at cases where the unit vectors are rotating. Okay, thank you.